2006, and I benefited greatly from that. So this is work which has been done over the years with a number of people: Pfrang, Govind Menon, Sheehan Olver, but mostly with Tom Trogdon. Also, we'll be speaking about work together with Stephen Miller. I'll come back to that later. So, so a few years ago, Pfrang, Govind Menon, and I initiated a statistical study of the performance of various standard algorithms to compute eigenvalues of random real symmetric matrices. In each case, the initial matrix H0 is diagonalized either by a sequence of isospectral iterates or by an isospectral flow. In the discrete case, as k gets large, hk converges to a diagonal matrix. So this means that given any epsilon, which is positive, there exists some first time k at which the off-diagonal elements of hk are of order epsilon, and hence the diagonal entries of hk give the eigenvalues of the original matrix to order epsilon. The situation is similar in the continuous case. Examples of such algorithms are well known. Here is the bare bones QR algorithm. You write H0 as Q0 R0, orthogonal, upper triangular. You flip them around, you get a new matrix which is clearly orthogonally equivalent to the original matrix. This matrix itself has its own QR factorization, etc. And then as you carry on in appropriate situations, HK converges. Toda algorithm is as following: continuum problem. You solve this ODE with initial data H0. BH is a strictly lower part minus its transpose. Now, both of these are completely integrable Hamiltonian flows, a fact which will play a role later. Now, the main finding was this in the paper with Pfrang, Govind Menon, and myself, which was rather surprising to us. And this is the key point. The fluctuations in the stopping times to achieve an accuracy epsilon turned out to be universal over a very wide range of assumptions for the ensemble of matrices you're interested in. So more precisely, for n by n real symmetric matrices H, chosen from an ensemble E, and for a given algorithm A and the desired accuracy E, or epsilon, you look at T, epsilon n a E, where H is a matrix chosen from the ensemble E, and this is the time for which it takes your algorithm A to achieve an accuracy epsilon for the matrix A chosen from E. And what you do is you look at the normalized stopping time. So for any matrix H, this is the time it takes to achieve accuracy epsilon with algorithm A. Then you look at this, which is the sample average over, say, 15 or 20,000 matrices, for which you're doing exactly the same thing. And this is the standard, the sample standard deviation. So this is the normalized stopping time. And then this is the point which I would ask you to really focus on, is that for a given algorithm E, and this is key, epsilon n must be in the suitable scaling regime. The histogram for this normalized stopping time is independent of the ensemble. In general, the histogram will depend on the ensemble, but for a given ensemble and epsilon n in the scaling regime, the histogram is independent of E. So this should put you in mind of the two-component universality in the classical central limit theorem, where once you fix the mean and you fix the standard deviation, you converge to a universal distribution. Now, here's an example of what one sees. On the left, you're going to see results of QR. This is bare bones QR, but you get a similar picture if you look at QR with shift. Then on the left, what you're looking at are two histograms, one on top of the other. The one histogram is obtained by doing QR to achieve an accuracy of epsilon 10 to the minus 10. N is the size of the matrix, is 100, but for two different ensembles. The one ensemble is GOE, so the entries are independent Gaussians, or they are Bernoulli, plus or minus 1. On the right, you have the Toda algorithm. Again, you have these two different ensembles. You have two histograms, one on top of the other. Here, epsilon is 10 to the minus 8, and n is 100. So you begin to see here that even for moderately sized matrices, you begin to see a universal curve coming out. Here you see a different one. And what I ask you to focus on here is that these two histograms are different. You don't get the same histogram for different algorithms. Now, subsequent to that earlier work, four of us, Govind Menon, Sheehan, Tom, and myself, raised the question whether these universality results were just a feature of eigenvalue computation. So, in particular, all our experiments initially were done with real symmetric matrices whose entries were independent. So then the first thing we did was to begin looking at more general eigenvalue algorithms such as Jacobi, and also algorithms for Hermitian ensembles, in which you have matrix entries which are no longer independent. For example, you could look at a matrix distribution, so e to the minus trace of, say, m to some power 2k dm, where the matrices will no longer have independent entries. And nevertheless, we found that the same phenomenon was present, this two-component universality, independent of your choice of ensemble. So at that point, we were rather optimistic or confident that this phenomenon of universality, independence of the distribution, was true for eigenvalue computation. Well, what about other fundamental algorithms? In particular, what about solving linear systems? So we looked at linear systems where H was random and B is random, and we used both conjugate gradient and Jumeriz, depending on whether the matrices H were positive definite or not. And again, we saw the same phenomenon coming through. So at this point, we were getting rather confident that basic numerical algorithms would have this feature of universality. Then we ask, well, maybe it's just a finite dimensional phenomenon. What happens if you get a bona fide infinite dimensional problem? So we looked at the following. We want to solve the Dirichlet problem, Laplacian U equals 0 on a random star-shaped region with random boundary data f. We chose it to be star-shaped because then the radius is a function of the angle. You can express in a power series, and or in a Fourier series, and if you choose your Fourier coefficients randomly, you're going to get random regions. So, and again, we found here that the phenomenon was present. So now we're thinking that these basic ideas, maybe they extend into infinite dimensional problems as well. The next feature we focused on is that all the algorithms we had looked at up to this point were really dynamical systems which were completely deterministic, and all the randomness was in the initial data. What happens if you have a bona fide stochastic algorithm? So one which, as you go along, you're flipping a coin and making different choices. So what we looked at is this wonderful algorithm, the genetic algorithm, to compute equilibrium measure for orthogonal polynomials on the line, or if you want to think about it, it's really the density of states for the Jacobi operator associated with the orthogonal polynomials. And there is a tremendous amount of randomness in such a problem. But again, we found that the same phenomenon was present. So even in bona fide stochastic algorithms, the phenomenon was still there. So at this point, we decide to raise the bar a little. So if you begin to believe that such a universality is a feature of computation, and if you believe the model or the idea that neuroscientists have, that the brain is just some kind of computer with software and hardware, then you should be able somehow to be able to see some kind of universality in neural computations. So how to actually do this, we didn't know initially, but then fortunately Bakhtin and Corel, Bakhtin was at Georgia Tech, is now a colleague of mine in New York. He had done some experiments with some volunteers at the University of Minnesota. So what did he do? Let me get to that point. I just want to give a little bit of detail here. Okay, sorry about that. If I had more time. So what he did, he got 46 participants. So how many people are here? Probably about 70, 80. He got 46 people, and to each one he showed 200 pictures. So each person saw 200 pictures. And each picture looked like this. And what the person had to do was decide, was it the picture on the left or the picture on the right that had greater area. What was recorded was only the time it took them to make a decision. So that means whether they got it right or wrong, didn't matter. How long does it take them to make a decision? So that means each person produced 200 times. You could turn that into a normalized histogram. And the remarkable thing is that at the level of these statistics we're dealing with, they were all coming up with the same histogram. There was a universality in what they were doing. This is what you see, for example. This is person 16, person 21, and so on. Then in a wonderful computation, Bakhtin and Corel used a Curie-Weiss model to derive a distribution, it's a Gumbel type distribution, which you see over here. So this began to give the idea that this idea of this universality is broader than just sitting behind a computer. So I'm not going to give, I don't have time to give the details of how it actually worked, but here's an interesting little fact. If you go onto Google, you can get from Google the time it takes for you to put in a request about a word in English, and it will give you the time it takes for that word to first appear in the answers. So you can get 3,000 English words with the time it takes to get a response. And what you get, as you see in blue, you get this histogram here for the times. If you use Turkish words, you get the same thing. And the distribution which Bakhtin and Corel got sits over here. There's some kind of universality there. I'm not going to press it. Now, up till this point, everything has been experimental. So if you're a mathematician, that means you have to do something, right? You can't just say, it's a lot of fun, but you have to really try and see if there is an algorithm of interest for which you can actually prove this universality. So the algorithm we chose was the Toda algorithm to compute the largest eigenvalue of a real symmetric matrix. So you've got a real symmetric matrix, H. Here's the Toda flow. And the stopping time we pick is the sum of the squares of the off-diagonal entries in the first row. So when these become small, less than epsilon, your matrix is basically deflated into a 1-1 matrix and an n minus 1 by n minus 1 measure. And what sits in the 1-1 position is going to be the largest eigenvalue, because the algorithm is a sorting algorithm. And what we found and what we proved is that if you look at this purely a random matrix statement here, you look at the difference between the two top eigenvalues, and you compute the distribution of this inverse difference of the largest eigenvalue. It's a non-trivial fact that for very large class of random matrices, typically Wigner matrices or invariant matrices, this limit exists. Beta equals 1. is the real symmetric case. Beta equals 2 is the complex emission. So this distribution exists. And what the results is the following. If you pick a number, fix any number sigma bigger than 5/3 and look at the scaling regime, so that for any n, epsilon must be sufficiently small, but n must still be large. Then if H is distributed according to, say, the Wigner distributions or invariant distributions, this is the result. So T is the time it takes for the total algorithm to compute the largest eigenvalue. And you see in the appropriate scale, that distribution is exactly giving this distribution I had in the previous page, which in words says the following. The time it takes as a random variable to compute the largest eigenvalue of a matrix is exactly, has the same distribution as the inverse of the difference of the two top eigenvalues. So this is a theorem which proves the universality. Now, let me just go back to one factor. It comes out from the theorem we proved that the expected time is n to the 2/3 log n. We believe this is a new result, not just a new result, but a new kind of result, because unfortunately so many of our results in numerical analysis are bounds, which have to take into account exceptional situations, so they very often are complete overreaches. They are far more than you actually need. But this is a very good situation, because you'll see here that the smooth line is the predicted times, the predicted histogram, and the rough thing there is what is actually observed. So what you actually observe is what is given by the theorem. Okay, just as a point of interest, if you look at epsilon equals 10 to the minus 16 and any n less than 10 to the minus 9, you see this is bigger than 5/3. So what that means in your typical laboratory computation that we all make, you're going to find yourself in that in the scaling regime. It's the right regime for day-by-day computation. Okay, so now, all right. So now I want to speak about. To give a little bit of a more philosophical twist to what we're saying. So as a backdrop to what I'm going to talk about now, consider the following interpretation of what we are saying. We're saying take an algorithm of interest, run it with random data, then something deterministic appears, this histogram, and that histogram is independent of whatever ensemble you're dealing with. So you can raise the following issue. First of all, given a process or an algorithm of interest, does it have such a universal histogram, or as we would like to say, does it have a signature? Secondly, is that signature descriptive? For example, if you have two different algorithms to compute the same object, will they have different histograms or different signatures? In other words, what we're aiming towards is, can you use signature to distinguish between different algorithms? So let me give following point here. Sorry about this. Okay. So look over here. On the left, you're looking at computations with the Jacobi algorithm. On the right, in the middle, you're dealing with QO. You're dealing with, on the right, you have total. This is a very low-dimensional system, 20 by 20 matrices. Now, somebody tells you, they give you a disk, and they say, use this disk to compute the eigenvalues of a matrix. You say, well, what algorithm do you use? And they say, it's proprietary. I'm not going to tell you. Okay, so how do you go about doing it? How do you do non-destructive testing on that? Well, you just run the algorithm on random data. If they said they were using some version of this, you say, no, it can't be, because I'm seeing this. So it's a way of distinguishing things by a method of non-destructive testing. So if you just permit me to make a lighter comment, right, is that how else do we determine a person's character except by how they respond to random events? Then we see what they're like. And we are so fine-tuned to it that we know very quickly if somebody is out of character. So I'll just put that out there. Okay. All right. Now, so what we decided to do is to try these ideas. Can these algorithms be used to differentiate between different situations in the cyber context? And so we want to see in particular, if you take RSA, which is the cyber algorithm of choice to generate a key, which is the basis for all our private interactions around the world. And as you know, the key to getting a key, a secret key, is to choose two large primes, P and Q. Not equal to Q. So that's the key. So what we focused on is the process of choosing two large primes. So we look for these primes in the region between, say, 2 to the n and 2 to the n plus 1. So these P and Q are chosen from there. And you can put down any distribution on 2 to the n, 2 to the that you want. And hopefully what we're going to see is some universality coming out of that. So bear in mind, as I was emphasizing, the universality results we spoke about always had two aspects to it. One was the size of the system, and which was n, and the other was the accuracy, which we call epsilon. And when epsilon n were in the right regime, you were going to see this universality. You should have in mind something like a physical phase diagram having pressure and temperature. If you're in the right regime of the pressure temperature diagram, you see a solid. A different thing, you see something else. So one should think of n as a size system and epsilon. In the case of eigenvalues, you knew what epsilon was, but what is epsilon here? What should play the role of epsilon? Well, what plays the role of epsilon is the following: is if I pick a number between there and there, how do I know that it's a prime? I picked a number. So addressing that question, one uses Fermat's little theorem, which says that if P is prime, then a to the P minus 1 is equal to 1 mod P. So you're looking at this number P, you pick a number A, you get a to the P minus, you see it's not equal to 1. It's not a prime. Pick another number, so it's out. But what can happen is that it's possible for P to be a composite number, not a prime, but still a to the P minus 1 can equal 1. For example, there are numbers called Carmichael numbers, the smallest of which, there are infinite a number of them. The smallest one is 561, which have the property that, so P is this Carmichael number, that a to the P minus 1 equals 1 for all numbers a which are prime with respect to P. So you could be unlucky. So what do? You got your number P and you want to test whether it's a prime. What you do is the Miller-Robin test, which goes like this. It's a more sophisticated version of Fermat's theorem, but I'm not going to go into too much detail. But what you do is the following. You look at a to the P minus 1, turns out to be 1. Then you pick another number A, and you test again. If after m such tests, then you haven't proved that it's not a prime, but you see it's pretty likely that it actually is a prime. So you can call the number of Miller-Robin tests that you take as being any number which passes m Miller-Robin tests. You can say it is an m-level prime. So what should epsilon be? Epsilon should be 1 over m. Because the more tests it passes, as it were, the more accuracy you have of it as a prime. Now, how does this algorithm work? So let me say it in words. Oh, okay, good. That's good to know. So what you do is the following. Okay, let me go here. So we're looking from 2 to the n, 2 to the n plus 1, and we have some distribution on the primes. And what you do is the first thing you do is you choose numbers x1, x2, x3, like that. And you take the number x1, and you begin a Miller-Robin test on it. It passes the first one, it passes the second one, then it's dead. It's out. Then you go to x2. It passes 1, 2, 3, 4, 5, and so on. If it fails before m tests, you throw it out. But you keep going until you find one which passes m tests. Then you keep it. You've got your first number. Then you start again. You'll get in, you make x1, x2, all choices from here according to that distribution. You look at x1 prime, does it pass one test? Does it pass two? You keep going until you find one of those numbers in exit which passes m tests. And you keep going in this way. And in this way, you're going to be led to a collection of x's, each of which are m-tested primes. And what you can do is you can record the time it took you to construct those. And that time involves choosing a prime and doing m tests. Now, a back-of-the-envelope calculation tells you that the normalized time it takes you to get m such primes is going to be distributed according to the probability of the time less than or equal to t is going to be given by e to the minus t plus 1. For t is 1 minus that, right? For t bigger than minus 1 and 0 elsewhere. Just elsewhere. So that's a back-of-the-envelope calculation that you should find. And what you'll see over here, so n, we're going from 2 to the n to 2 to the n plus 1, and you're looking at these normalized running times. So in n, the red curve is this exponential starting at minus 1. And what you see, and there are two histograms which correspond to choosing two different measures on that interval. And you see that as n gets bigger and bigger, you begin to get closer and closer. You begin to get into the scaling regime. So you begin to believe that this process does have universality. So how can one use this? So this is all connected, what I'm presenting, with choosing one prime. As I said, RSA requires you to find two primes independently, right? So the distribution of two independent primes is just the convolution of these two things. Now, how can you use this? Well, suppose you want to send a message. You can buy a little card made by a company called Infinon, for example, and you plug this card in, and it will give you an RSA code, it will give you your own key. It will give you a key. Problem is, it's a commercial object. So it's small, it's too small to do the full sampling between 2 to the n and 2 to the, so it cuts corners. So how can you know it's cutting corners? Well, you can test it against what you should be seeing. And what you see is the following. Now, the green is the convolution of these two distributions. The step green is what you actually see if you choose two primes following this full procedure. But if you plug in this infinite card, you'll get a distant difference. So you can tell the difference. You can see that something's actually going on. So let me end off by saying the following. My first thing is to urge everybody to take their favorite algorithm and see whether it has this universality feature. Is that, let me say it in a little bit of a little bit more mysterious fashion, is that every algorithm has buried in it a secret. That secret is behind a closed door. And if you want to open the door, the key is to look at your algorithm on random initial data. Okay, thank you.
First, for the psychology experiments,
Yeah.
is there a notion of a relation for that problem between accuracy and size?
Yeah. Yeah. So okay. So then there. So let me phrase it properly. Then, well, it comes in the following way. So think about it like this: is that how would you build a model of this? Remember, people are making decisions. How do you make decisions? Well, you say maybe it's a this, then you think some more. You say maybe it's a that, maybe it's a this, maybe it's a that. So what it means is you can have a state space, which is a vector of size n, whose entries are plus or minus 1. So plus 1 means you think it's the right, and minus 1 thinks the left. Now you add it up. Now you're only going to get a non-zero number if you're beginning to think more that it's a plus 1 or more than it's a minus 1. So the size comes in the size of what that sum is. That's where the absolute.
No, the size I understood,
but that plays the role of the accuracy, because you can make it bigger and bigger. The bigger that is, the more accurate it is. Okay. Yeah.
In the decision-making process, the solution was the Gumbel
Yeah.
solution.
Yeah.
And this puts a red flag on the connection to the discrete value field.
Yeah.
Has this been explored?
It's certainly in everybody's mind. So you've got universality of expressed in terms of the Gumbel in these many different experiments. Why is it, why is it in people's minds? What are they doing there, right? What is it in this actual model on this Curie-Weiss model? Or what is it in the Google what is that exactly? It's a very good question. Can I pin down exactly why we are Gumbel, as you're saying, is well known as the result when you look at maximum of a set of independent variables. What exactly that is, it's a very interesting question.
Let's postpone further questions to the
Okay.
Meanwhile, let us thank Percy for a fascinating.
Thank you.